All right, welcome. Today we are diving headfirst into something really cool in reinforcement learning. We're going to talk about a super elegant technique that actually bridges the gap between two of its biggest ideas, temporal difference learning and Monte Carlo learning. So let's kick things off with a question that every single reinforcement learning agent has to grapple with. Do you want to be a fast learner, someone who makes a judgment call after every single step? Or do you want to be more of a deep thinker, patiently waiting until the whole game is over to really understand what happened? That's the trade-off, right? And that's exactly what we're going to unpack and solve today. Okay, so here's the game plan. First, we'll lay out this core dilemma between TD and Monte Carlo. Then, we'll look at a simple way to bridge that gap, and then an even better way using something called eligibility traces. And finally, we'll see how these traces work in the wild for both on-policy and off-policy learning. All right, Section 1, the RL dilemma. TD versus MC. This really gets to the heart of a fundamental trade-off in learning, bias versus variance. So, on one side of the ring, you've got temporal difference, or TD learning. This is our fast learner. It updates its beliefs after every single step. It does this by bootstrapping, which, is really just a fancy way of saying it takes a guess based on its current incomplete knowledge. It's super fast, but that guess could be completely wrong. That's what we call high bias. Then on the other side, we have Monte Carlo, our deep thinker. It patiently waits until the whole episode is done, until it knows the actual final score. This is super accurate, low bias for sure. But man, you have to wait forever, and any one game can have weird random stuff happen, which gives it high variance. Okay, so how do we get the best of both worlds here? Well, the most intuitive first step is to just find a middle of ground, right? Instead of updating after one step or waiting for the entire episode, what if we just wait for a few steps? And that, right there, is the whole idea behind end-step returns. And the idea is actually, beautifully simple. Instead of taking just one real reward and then immediately guessing, like in standard TD, we say, hold on, let's collect n steps of real, actual rewards. And then only after we have that chunk of real information do we make our guess, our bootstrap about the value of the state we ended up in. So let's see how this actually gets built. It's really just adding things up. We start with the very next reward, then we add the one after that, but we discount it a little with gamma. We keep doing this for n steps, and then at the very end, we tack on our guess, our bootstrapped value estimate from that future state. And of course, that guess is discounted a lot because it's n steps away from where we started. Okay, quick pop quiz to make sure we're all on the same page. Take a look at these formulas. If we're doing a 3-step return, so n is 3, which one of these is the right way to write it out? Just think back to how we built it. And yep, the answer is B. It's pretty straightforward, right? You sum up 3 real rewards, and then you bootstrap from the state you land in, which is S of t plus 3. So n-step methods are great. They give us this nice, simple knob to turn between TD and Monte Carlo. But there's still a catch. You still have to wait those n steps before you can make your update. Can we do better? So let's move on to a much more elegant solution, a way to get this same kind of blending effect, but one that works online. I mean, at every single time step, with absolutely no waiting. And we do this with a really beautiful idea called eligibility traces. Okay, this is a seriously powerful concept. Just imagine this. Every time our agent visits a state, it leaves behind a little memory trace, like a footprint in the sand. And over time, that footprint starts to fade away. Now, why is this useful? Well, when something important happens later, a big reward or a big penalty, we can look back along this fading trail of footprints and assign credit or blame to all the states that led up to that moment. It's like a trail of responsibility. So there are 2 ways to think about this, and this is important. There's the forward view, which is kind of the theory behind it. It says our target is this super clever weighted average of all the possible n-step returns. But to actually calculate that, you'd still have to wait until the episode is over. So not super practical. But then there's the backward view. This is the practical magic. This is what we actually do. It uses that eligibility trace, that trail of footprints, to update all the past states based on the error we see right now at this very moment. And here's the kicker. The math works out to be exactly the same. We get the benefit of the forward view with the speed of the backward view. And this table just shows how brilliant this whole thing is. We now have this one little parameter lambda that acts like a dial. You can literally turn it. If you set lambda to 0, those memory traces fade away instantly. Boom, you're just doing 1-step TD. Now crank that dial all the way up to 1. The traces never fade. And guess what? You're doing pure Monte Carlo.
And for any setting in between, you get this beautiful, smooth mixture of all the end-step returns. It's one unified algorithm. Okay, this is great. We have this amazing mechanism for assigning credit over time. But how do we use it to actually learn how to act, to find the best policy? Let's see it in action, starting with an on-policy method called SARSA lambda. And on policy just means we're trying to improve the same policy that we're using to explore the world. Now, when you go to actually code this up, you have a choice to make. You can use accumulating traces, where every time you visit a state, you just add one to its trace. The problem is, if you get stuck in a little loop, that trace can grow bigger and bigger and bigger, and your updates can become really unstable. So what people often do instead is use replacing traces. The rule is simple. Every time you visit a state, you just stamp its trace back to 1. It keeps things from getting out of control and generally just works better and is more stable. All right, here's a subtle but really, really important detail. For control, for learning what actions to take, our traces aren't just on the states, they're on state action pairs. So think about this. What if you're in state S, you take action A1, but then later you end up back in state S, and this time you take a totally different action, A2? What do you do with the trace for that first action, A1? Well, the logic is pretty clear when you think about it. The rewards you're about to get, they are a consequence of the new action you just took, A1. It would be completely wrong to give any credit for that future outcome to some other action you took in the past. So you have to clear the traces for all those other actions from that state. It's all about making sure credit is assigned to the right decisions. All right, on to the final piece of this whole puzzle, off-policy control. See, everything we've talked about so far kind of assumes our agent is following its game plan. But what happens when it goes off script? What happens when it's exploring and takes a random action, one that its current best policy would never have chosen? This right here is the central challenge for an off-policy agent like Q-learning. And the classic algorithm that tries to solve this is called Watkins's Q-lambda. The goal is to get the best of both worlds, the power of Q-learning, which always learns about the optimal path, combined with the awesome efficiency of eligibility traces. So remember, Q-learning is all about learning the value of the best possible greedy path. So what happens to our nice, neat credit trail when our agent takes a detour? When it deliberately wanders off that optimal path just to see what's out there? The answer is pretty dramatic, but it's simple, and it's correct. You have to cut the trace. Just sever it. The moment the agent deviates from that greedy path, that credit trail you've been building up is no longer valid. It doesn't predict what's going to happen on this new exploratory path. So you have to reset it. And that's the core logic behind Watkins's Q-lambda. Look, you always do a normal one-step Q-learning update for the action you just took, no matter what. But then you check, was that the greedy action? Was that the best action according to my current policy? If yes, awesome, the trace decays normally. But if it was an exploratory, non-greedy move, you immediately reset the eligibility traces for all state action pairs back to 0. And this has a really interesting side effect. If you explore too much, you're constantly cutting your traces, and your fancy TD lambda algorithm basically just turns back into slow, simple, one-step Q-learning. Now, Watkins' method is a bit of a blunt instrument, right? A hard reset. More general off-policy methods handle this a little more gracefully. They use a mathematical tool called an importance sampling ratio to correct the trace at each step. You can just think of this ratio as a number that asks, how likely was it that I would have taken this action under my target policy? If you take a really wild exploratory action that your greedy policy would almost never choose, that ratio becomes tiny, close to 0. And what does multiplying by 0 do? It effectively cuts the trace, but it does it in a much softer, more gradual way. So, let's end with a final thought for you to chew on. After all this, you now have this one incredibly powerful dial at our disposal, Lambda. You can tune the entire learning process from fast and biased to slow and accurate. So my question to you is, if you were training a robot to solve a simple maze, where actions have immediate consequences, where would you set that dial? And what about for an AI playing millions of games of Go, a game with incredibly deep, delayed consequences? Your answer to that question really gets to the heart of why bridging this gap is so incredibly powerful.